Log on, tune in, find out. Another good idea from Cambridge.
Chuang, who will give his first talk on sl2 categorifications.
I'd like to thank the organizers, especially the one who's here, for giving me the opportunity to give this series of talks. I'll explain these three lectures. One approach to the categorification of sl2 models. And the plan of the three lectures is as follows. In the first, I will give some motivation. In the first talk, I will give some motivation for why we want to consider these categorifications, and especially why we want to use them to construct some equivalences of derived categories. And this motivation comes from the representation theory of finite groups. And this will allow me to also delay saying exactly what I mean by categorification. And in the second, having given that one example, I will give the definition of this version of categorification, which Raphael Ruquier and I developed. And we called it sl2 categorification. And the idea here was to come up with a sort of enrichment of the theory of the representation theory of sl2, where we replace the representation spaces by categories. Now, next week, Raphael Ruquier will discuss in his lectures a more sophisticated scheme, which is valid not just for sl2, but for Kac-Moody algebras in general. And he takes a slightly different viewpoint. Okay, but I'm going to stick with this, this original formulation, which is convenient for the example that we want to consider and for the construction of the derived equivalences, which is the focus here. So having, with this definition, I will then describe how to construct and prove the existence of the derived equivalences. And then I'll explain how these derived equivalences are of a very special type, which perhaps is not immediately obvious from their construction. And we call these type of equivalences perverse equivalences. And the third lecture will be a description of a sort of general theory for these type of equivalences. Okay, so let me start with the motivation coming from finite groups. And I'm going to arrive at a conjecture of Michel Brouet, for which the attempts to prove this conjecture in certain special cases led to the idea of this sl2 categorification. And this conjecture is known as Brouet's abelian defect group conjecture. Okay, so I'm going to give a quick review of some notions in the modular representation theory of finite groups, just in case some of you aren't so familiar with it. Okay, so we want to consider the representations of a finite group over an algebraically closed field. And of course, this is the same as considering modules for the group algebra. Okay, as Meinhof mentioned, the most familiar case is when the characteristic of K is 0. For example, when we take the complex numbers. And there, the theory is well developed, and we know that, for instance, the group algebra is semi-simple. So, from the point of view of homological algebra and things like derived categories, it's not going to be so interesting. Okay, and so we're going to be more interested in the case when the characteristic is positive, when we're in a field of positive characteristic. Okay, but let me just remind you that because of the Wedderburn structure theorem, in the case when the group algebra is semi-simple, for example, over the complex field, then we get a decomposition of the group algebra into a product of matrix algebras. Okay, so we can write the group algebra as a certain product okay, so here the notation, this is just the algebra of n1 by n1 matrices over the complex numbers. Okay, so now when we go to consider the case that the field has positive characteristic, okay, so let's consider that case now. Okay, then the group algebra can be non-semi-simple. Okay, in fact, that happens precisely when P divides the order of the group. Okay, so we're not going to get anything as nice as a decomposition into a product of matrix algebras, but as a first step, we can just try to mimic this decomposition as much as possible. So we can still write Kg as the product of algebras. Okay, so what I do is I decompose it as a product until I can't go any further. So each of these Bi cannot be themselves written as a product of algebras. Okay, and these are called, once we do this, these are called the blocks of Kg. Okay, and so in the case that we're working over the complex field, these matrix algebras would be the blocks. Okay, but here, having decomposed the group algebra in this way, then the representation theory of the group is just reduced to the study of the representation theory of each of these blocks individually. We could write, for example, that the abelian category of modules is equivalent to the product of the corresponding categories for the blocks. Okay. Let's do an example of what these blocks look like for a small group. Let's take the symmetric group on 3 letters. Okay, then in the case where P is greater than 3, the group algebra is semi-simple, just as in the case of the complex field. And we get the sizes of these matrix algebras are 2, 1, and 1. Okay, if P is equal to 2, then we still get a matrix algebra of 2 by 2 matrices. Okay, but we only get one other block, okay, which is not semi-simple. It's the algebra, 2-dimensional, non-semi-simple algebra. We can take it to be polynomials in one variable modulo the square of that variable. Okay, so that's perhaps the first interesting non-semi-simple example. And finally, when P equals 3, then there is only one block. Okay, there's no decomposition possible. Okay, so you see that in the modular case, we can still have matrix algebras appearing. Okay, but we get other blocks which are not matrix algebras. And it's useful to try to measure how far each block is away from being a matrix algebra. Okay, and that is the job of the defect group. Okay, so a defect group of a block B is a subgroup of G such that every module for B is a summand of a module induced from that subgroup. Okay, and we also want it to be this subgroup to be minimal with respect to this property. Okay, then it's easy to show that such a subgroup has to be a P subgroup of G. Remember, P is the characteristic of the field, and that all such subgroups must be conjugate in G. Okay, and then as I said, the subgroup D measures how non-semi-simple B could be. So to start off, D is the trivial subgroup if and only if B is a matrix algebra. And the next case of interest is when D is a cyclic group. Okay, and here it's known that the this is equivalent to saying that there are only finitely many indecomposable B modules up to isomorphism. Okay, by indecomposable, I mean it can't be written as a direct sum of two non-trivial submodules. Okay, of course, in the case when B is a matrix algebra, then every module, every finite dimensional module, is a direct sum of the unique irreducible module. So in that case, there's only one indecomposable module up to isomorphism. Okay, so once we have a defect group, then we can associate to the block a block of a potentially smaller subgroup. Okay, so each block B has what's called a Brouwer correspondence. Okay, which is a block of the normalizer in G of the defect group. Okay, in fact, there's a one-to-one correspondence between the blocks of a group with a fixed defect group and with the fixed defect group D and the blocks of the normalizer with that same defect group. Okay, but let's not worry too much about that. At this point, I'm just associating to B another block of a subgroup. Okay, and then the obvious question is, what is the relationship between B and C? And at least when D is abelian, one can make some guesses. So we have conjecture of Alperin, which says that in this special case that D is abelian, then the block and its Brouwer correspondent have the same number of simple modules. Up to isomorphism. Okay, so let's look at a couple examples. Let's consider the group to be the alternating group of degree 5 at the prime 3. Okay, then there are 3 blocks, only one of which is not a matrix algebra. Okay, we have 2 matrix algebras of degree 3. And just this one here, which is not semi-simple. Okay, since it's not semi-simple, its defect group is non-trivial. Okay, at the same time, it has to be a P subgroup. But here, the sl2 subgroup is already just of order 3. So we know that the defect group has to be of order 3. Cyclic group of order 3, and its Brouwer correspondent is going to be a block of the normalizer, which in this case is isomorphic to the symmetric group of degree 3. Okay, as we saw in this example here, when p equals 3, the S3 only has one block. So that means that C must be all of the group algebra. Okay, so its bar correspondent is the group algebra is the group algebra of the normalizer. Okay, and the prediction of Alperin is that B and C should have the same number of simple modules, and it's easy to check here that both these have 2 simple modules. Okay, and in this case, there's a very good explanation for it. Okay. Now, the easiest explanation would be that the blocks are isomorphic algebras. Okay, then of course the representation theory would be modules over one would be the same as modules of the other, and you would deduce that the simple modules for one was the same as simple modules for the other, and they would have to have the same number. Okay, here that can't be the case because you can calculate the dimensions of the two and see that they're different. This is 6-dimensional, while this one is bigger. Yeah. Okay, but there still is an equivalence between their module categories. Okay. So the explanation here is that these two are Morita equivalent algebras. Okay, that is to say, there's an equivalence between their categories of modules. Okay, now in the category of modules, one can pick out the simple objects just by using the language of the categories, okay, of the language of morphisms. So that means that an equivalence of the categories is going to have to preserve simple objects. Okay, and so from that one can get the numerical consequence from this. Okay, now let's look at the same group but at a different prime. The prime 2 now. Okay, here we get one block which is not semi-simple. And the defect group is isomorphic to an elementary abelian group of size 4. Okay, so it's a product of two cyclic groups of order 2. And the normalizer is again indecomposable. Okay. The bar correspondence is a block of the normalizer, which is isomorphic to the alternating group of degree 4. Okay, so, and again, the prediction is correct because both these blocks have 3 simple modules. But unfortunately, we don't have the handy explanation of the previous example. Okay, there's no equivalence of the module categories. Okay, but and this is where we need the derived category to help us with the explanation. Okay. Instead, Ricard showed that proved that there is an equivalence of the derived categories of these abelian categories, the derived bounded categories. Okay, in a moment I'm going to explain why we can deduce from this that B and C have the same number of simple modules, but it's not because simple modules are preserved by this equivalence. Okay, as Pramod explained, once you go to the derived category, it's no longer an abelian category, so things like sub-object and quotient don't make sense. So you can't pick out what the simple objects of B mod viewed as complexes in the derived category by just using the structure of the category, even if you add the triangular structure. Okay, to show you an example of what this equivalence looks like, I'm going to write down what happens to the simple objects in the derived category when they go over here for the equivalence that Ricard constructed. Okay, so we have three simples on both sides. Let's call them S1, S2, and S3. Okay, so Ricard's functor, his equivalence, preserved one of the simple modules. So this simple module gets sent to a corresponding simple module here, T1. Okay, remember I'm regarding, these are the simple modules for B regarded as objects in the derived category by placing them in degree 0, say. Okay, but these two simple objects do not go to simple objects for C. Okay, instead, here we get a non-split extension of T1 by some other simple module. Okay, so by this picture I mean a non-split extension of T1 by T2. Okay, so T2, there's a submodule of this isomorphic to T2. Okay, but that embedding doesn't split. And this has to be shifted in degree by 1. Okay, and similarly, this last simple module gets sent to a non-split extension of the first simple module by the last one, again shifted by 1. Okay, so on this side we have the three simple modules here under the equivalence go to things which don't look so simple. Okay, but this might be a good practice for calculations in the derived category. For example, by Schur's lemma, the endomorphism ring of, say, S2 has to be just one-dimensional. Okay, and so the same thing must be true on this side. Okay, and that's an easy calculation over here. Similarly, you can compute homomorphisms between simple modules, and you should get 0 if they're not isomorphic. And here, say the harm between these two becomes some kind of calculation of x on this side. Okay. Now, of course, this is just an instance of a more general guess that we can have, which was made by Brouet. Okay, under the same assumption that the defect group is abelian, then a block and its bar correspondent should be derived equivalent, i.e. there's an equivalence of there's a equivalence of triangulated categories of the derived categories of the two algebras. Okay, and this, to explain why this implies the earlier conjecture of Alperin, I need to remind you about the notion of a Grothendieck group of an abelian category. So let's recall that given an abelian category A, then we define the Grothendieck group is we take the free abelian group on all the objects of A. Okay, and we use the symbol, we associate to each object a corresponding symbol in the group. Okay, and then we mod out by some relations given by short exact sequences. We have the relation y is equal to x plus z for all short exact sequences x, y, z in A. In the type of examples we're considering, where objects have composition series, then we can use the simple modules, or the classes of the simple modules, as a basis for the Grothendieck group. So for a block, or in more generality, say a finite dimensional algebra, this is a free abelian group on the classes of simple modules. Okay, so here we're taking the sum over all isomorphism classes of simple B modules. Okay, and you can see that by the way it's defined, if we have an exact functor between abelian categories, then we get a homomorphism between the Grothendieck groups. And an equivalence will give an isomorphism of Grothendieck groups. So notice that if we have an exact functor, then we get a induced homomorphism. Okay, in particular, if we have an equivalence we get an isomorphism of the Grothendieck group. Okay, so of course that implies that the two abelian groups have the same rank and therefore the same number of simple modules. Of course, this is a much more direct argument. Is the simple modules have to go to simples, as I described earlier, and this preserves Okay, now when we go to the derived category, we can still define a Grothendieck group. And therefore, we can come up with a similar conclusion. With the important difference that the simple modules are no longer recoverable. So even though we get an equality between the number of simple modules, we don't get a bijection between them. Okay, so if we take now instead a triangulated category, then we can define the Grothendieck group in exactly the same way. Okay, but of course we replace the short exact sequences by distinguished triangles. Okay, and it's again the case that, okay, maybe then I should remark on the special case where we have the derived category, which is the prototypical triangulated category, which Pramod introduced this morning. Let's recall that okay, so going back to the case where A is an abelian category. Okay, then A embeds as a full subcategory of its derived bounded category. Okay, and this induces an isomorphism between the Grothendieck groups. Okay, and the way to see this is that any object, okay, I guess to see that this is surjective, one notes that if you take any object inside the derived category, then its class in the Grothendieck group is just the alternating sum of its homologies. It's the sum of -1 to the n h n. Okay, here we're using the fact that we're looking at bounded complexes with bounded homology. Okay, so that shows it's surjective, and it's not much more work to show that you actually get an isomorphism here. So one sees that the derived category of, say, the modules for B again contain the information of how many isomorphism classes of simple modules there are, namely in the rank of this abelian group. So we conclude that a derived equivalence between two algebras gives an equality of the number of their simple modules. Okay, so an equivalence implies an equivalence, an isomorphism between the Grothendieck groups of the derived categories, which can be identified with the Grothendieck groups of the underlying abelian categories. Okay, but as I said before, once we go to the derived category, the simple objects are lost. So this may not, okay, but this isomorphism, the classes of simples may not be preserved. So by going to the derived category, we get a bit more flexibility because we can consider complexes now. But the structure is still tight enough that even though we've lost the notion of simple object, their number is still encoded inside the category. Okay, good. So let me now go to talk about Brouet's conjecture for a particular class of groups. Okay, even though now we know that Brouet's conjecture is true for quite a good number of classes of groups, the methods of proof seem to be different for each example. But in the example of the symmetric groups, this idea of categorification plays a role in the proof. Okay, so let us consider blocks of, let's consider two blocks of symmetric groups. Okay, I'm going to take two blocks which are not necessarily in the same group algebra. Okay, so I allow to change the degree. Okay, each of these we choose a defect group and get a Brouwer correspondent. So we have defect groups and a Brouwer correspondent. Okay, so the situation of Brouet's conjecture is when D is abelian, but for the time being, let's not place any restriction on the defect groups. Okay, then it's true that the just knowing the defect group allows you to figure out what the broad correspondence is up to Morito equivalence. So it's a fact that the defect groups are going to be isomorphic if and only if the broad correspondence are Morito equivalent. Okay, so in the case when D is abelian, that has the effect of saying that basically if D is abelian, then Brouwer's conjecture predicts that each block is going to be derived equivalent to its broad correspondent. Okay, but if the defect groups are in fact isomorphic, then those two broad correspondents are not only derived equivalent but Morito equivalent. So the two blocks must be themselves derived equivalent. And we can use this as a way of as a shortcut to proving Brouwer's conjecture for all blocks. Okay, so given a block B which has a abelian defect, okay, it's always possible to choose. It's always possible to prove Brouwer's conjecture, not for B, but for another block with the same defect group. Brouwer's conjecture can be proved for some other block with the same defect group. Okay, and it can be chosen in such a way that that is easier to, relatively easy to prove. Okay, so this is the proof of Brouwer's conjecture in this case goes by some combined works of Ricard, Marcus, and some joint work with Rada Kesser. Okay, finding this B dash is not obvious. One has to choose it quite carefully. And this choice was suggested by Ruquier. Sometimes this is called, in this context, Ruquier block. Okay, and having proved it for this one block, then this fact here means that to prove it for all the other blocks of the same defect just amounts to proving that all blocks of a fixed defect are derived equivalent. Okay, so Brouwer's abelian defect group conjecture for blocks of symmetric groups follows from the theorem, which is the main subject of these lectures, the main application, I should say. This is joint work with Ruquier. that two blocks of symmetric groups are derived equivalent if and only if their defect groups are isomorphic. Okay, so this theorem is true for arbitrary d. It doesn't have to be abelian, but it's only when it's abelian that, of course, that it is going to have some bearing on the abelian defect group conjecture. One can try to speculate what sort of general theorems one might try to, what general conjectures one might try to make about blocks of groups when the defect group is not abelian, but so far, as far as I know,
So how do
we
you
don't know.
connect the B and C?
B and okay, right. So you prove for so you start with B, and you want to prove that B and C are derived equivalent. Okay. Now you choose some other block B dashed, for which you already know how to prove Brouillet's conjecture. It's somehow easier. Okay, so there you know that B dashed and C dashed are derived equivalent. Okay, but from what I said here, C and C dashed are derived equivalent. Okay, so by going around, you only have to prove that B and D dashed are derived equivalent. Does that make sense? Okay, and finally, I'm going to explain briefly how one starts to prove this in the language of categorification. Okay, so to connect these blocks of various different symmetric groups, I'm going to need functors between their module categories. And of course, the way I can get from between symmetric groups of different degrees is to induce and restrict. So one idea is to put all the representation theories of all these symmetric groups together. Okay, so I describe now sl2 clear. Okay, so if I take a module for Sn, then by restriction, I get a module for Sn minus 1. Okay, since I can do this for any index n, I can just think of this as a functor, an endofunctor of a certain category where I put all these abelian categories together. So I take f to be the product or the direct sum, say, of all the module categories of all the symmetric groups. Okay, then I've defined here a functor, which I could just call restriction. Okay, any object here is going to be a direct sum of modules for various different symmetric groups, and I restrict them all, and again view it as an object here. And of course, I can do the same thing for induction. Okay, and now using a method of Robinson, I can refine these functors somewhat. So having restricted from Sn to Sn minus 1, anything in Sn which commutes with every element of Sn-1 will still act on the restriction. Okay, of course, there are no such elements. Okay, but I can work inside the group algebra instead. Okay, so any element of the group algebra of Sn which commutes with every element of Sn-1 will still act on the restricted module. Okay, and this contains the so-called Murphy element, okay, which is the sum of transpositions 1n, 2n, through n minus 1n. So this restriction has this additional operator acting, so I can split it using the eigenvalues for the action of Ln. So I define EAM to be the A generalized eigenspace for the action of Ln. Okay, so this is defined for A, any scalar. Okay, but as it turns out, all the eigenvalues lie in the prime subfield. So that means that this restriction functor decomposes as a direct sum of P functors. And we can use the fact that induction and restriction are adjoint to decompose the induction functors in an analogous way. So we get various exact functors on this abelian category F.
I'm sorry, when you say res, that's the sum of all the restrictions to one less?
That's right, yes, sorry, just one less, always to one less. Okay, and then the result which starts the whole story off, the whole categorification story off, is that when we pass to Grothendieck groups, so how should I say this? The action of these operators let's call them on the Grothendieck group. On the Grothendieck group of F. It extends to an action of a Kac-Moody algebra, okay, where these are the usual Chevalley generators. Extends to an action of the action of the affine Kac-Moody algebra extended SLP. Okay, and the weight space decomposition with respect to this action is exactly the decomposition into blocks. Okay, moreover, the Weil group of this Kac-Moody algebra is going to act on the weight spaces. And it acts transitively on the weight spaces, which we can identify with blocks, which have a fixed defect group. Okay, and the Weil group acts on weight spaces equals blocks transitively on blocks of a fixed defect group. Okay, so in other words, this action of this Weil group should be used to somehow produce the necessary derived equivalences. Okay, and this Weil group, since it's generated by certain reflections, we just have to prove that each reflection corresponds to a certain, can be used to construct a derived equivalence. Okay, but each of these reflections is just coming from one pair of E and F. Okay, so that's just a problem to do with sl2. Okay, so next week, Ruquier is going to talk about more general categorifications. But for the purposes of this problem, in order just to get the needed result, it suffices to consider just the action of sl2. And I'll explain how the what sort of formalism that one needs to develop to carry this out next time.
Thank you very much. Are there questions, remarks?
What module do we get?
I'm sorry?
So what module is K?
Oh, this is, I guess it's the basic representation. No, I suppose this is not quite right. I guess if we just work over the complex numbers, so if I complexify these Grothendieck groups, then that's the highest way reduced. But this is not the integral form of that representation. It's dual to that.
The affine Weil group here is, this Weil group is the affine Weil group
It's-
for SLP hat.
That's right. It's the affine symmetric group.
And so are you saying that for each, if I look at the blocks with a fixed defect group, that's an orbit, a W orbit?
Yeah, that's right. Yeah.
But those are not finite.
The orbits?
We've got everything put together, so it's not finite.
That's right. Yeah, it's not finite. Yeah.
Further questions? Seems to be the case. Then we have a break of almost half an hour, and then the problems or discussion sessions will start.